Hello everybody, welcome into another lesson. So today we are going to talk about determining the determinant of a square matrix. And for one, in order for a matrix to have a determinant, it has to be a square matrix, meaning it has the same number of rows as it does columns. Well, what is the determinant of a matrix? The determinant is simply a single numerical value associated with that matrix. They have uses such as finding the inverse of a matrix, or in the future coming up, we're even going to have a method called Cramer's rule, which will enable us to solve a system of equations. They can also help you find the area of a triangle, the area of a parallelogram. They can also help you test for collinear points. There's many other uses for determinants, but today we're just simply going to find determinants. So up here first we have the rule for finding the determinant of a 2 by 2 matrix. So if you have some matrix A, order 2 by 2, you have entries A, B, C, and D. The notation for determinant you'll often see is det A, meaning determinant. To find the determinant, you'll convert the matrix into what looks like absolute value notation, and you'll keep your entries the same. So instead of using these brackets, you'll use what looks like absolute value symbols. The determinant of a 2 by 2 is AD minus BC, and that may look familiar to you because we did 1 over AD minus BC to find the inverse of A when we were talking about the inverse of a 2 by 2 matrix. And in fact, that's part of how we find the inverse of a 2 by 2. But let's do some examples of a 2 by 2 determinant. So let's say we got some matrix A with entries. Actually, let's do a 1 by 1. 1 by 1s are really easy. Let's do a couple 1 by 1s. Let's say matrix A is a 1 by 1 matrix with entry 1. Well, the determinant of A is literally just going to be the entry inside. Now, this determinant thing does not necessarily mean the absolute value. It's literally just going to be the number inside, which would mean the determinant of that is 1. Alright, now let's say we have matrix A is another 1 by 1 matrix with entry negative 10. So the determinant of A, again, is just simply you convert it to what looks like absolute value notation, and it's going to be the entry that's inside of the matrix, and it would be negative 10. So the determinant of A would be negative 10. Those are 1 by 1s. Now what about 2 by 2s? So let's start with some of those. So we have matrix A has entries 6, 2, negative 5, and 3. So we have a 2 by 2 matrix. We want to find the determinant of A. Well, you're going to take everything in your matrix, convert it into what looks like absolute value notation, though it's not really an absolute value. This is how you work on a determinant. So now we're going to take AD, in this case, which is 6 times 3, minus your B times C, so minus 2 times negative 5. Well, this would end up turning into 18 plus 10, giving you the value of the determinant to be 28. So the determinant of matrix A ends up being 28. And I got a couple more 2 by 2s, and then we'll move on to higher order determinants. Those are dealt with a little bit differently. All right, 3, -3, 4, -8. So matrix A has entries 3, -3, 4, -8. Again, we want to find the determinant of matrix A. So we'll convert this into what looks like absolute value notation. We'll have 3, -3, 4, -8 inside of what looks like absolute value notation. So now you just take AD, so that's going to be 3 times -8 minus that B times C, so that'd be minus -3 times 4. Well, this turns into -24 plus 12, giving you the determinant of matrix A to be -12. So matrix A's determinant is -12. Let's do one more 2 by 2. All right. Let's pick -7, 6, 1/2, and 3. So matrix A has entries -7, 6, 1/2, and 3. So let's go ahead and find the determinant of matrix A. Well, that's going to be, you're going to, of course, convert all of your entries, keep your entries the same, but use this absolute value looking notation to indicate that you're taking the determinant of the matrix. So now you're just going to take A times D, so that would be -7 times +3 minus your B times C, so that'd be -6 times 1/2. So you should get -21 minus 3, which would mean the determinant of this matrix is going to be -24. So the determinant of A in this case is -24. Okay, so those are 2 by 2 matrices. I think those are pretty easy. What we need to deal with now is when we get into 3 by 3 or higher. So let's set this up here. Let's say a 3 by 3. All right, so we're going to have matrix A has some 3 by 3 entries. A, B, C, D. I'm going to skip E because I don't want to use E since it actually has a numerical value. Same with I. All right, so here's a 3 by 3 matrix, matrix A. All right, we want to find the determinant. But first, what I'm going to do is set up what's called a coefficient determinant. And this is going to make sense in a minute. I'll explain these plus and minus signs in just a minute. But if we want to find the determinant of a matrix 3 by 3 or greater, here's what we have to do. You can use two methods. You can either go up and down the column or up and down the row. It really doesn't matter. But once you stick with the column, you got to continue down the column, or if you stick down the row, you got to continue down the same row. And you can pick any column or any row to do it. It doesn't matter. You just got to stay in the same row or same column while doing it. So let's say I go down the first row, right? So the determinant of A, I'm going to definitely take all the entries, put it into absolute value notation. A, B, C, D, F, G, H, J, K. All right. Now, how you're going to do this, let's go down the first row. This is going to be equal to the first entry in the first row. You have A. This pairs with your coefficient determinant. So every entry is alternating positive and negative. So we're going to take positive of A times, now what you want to do maybe to help yourself temporarily is strike out the column and row that you're working down. You're going to get a resulting 2 by 2 determinant times your entry A. So that would be the determinant of FG. Let me write that in black. So it's the determinant of whatever's left over. So F, G, J, and K. All right, so we've just figured out the first part of it. I'm going to have to rebuild this here. I'm going to have to rebuild this a few times to show you, but we'll do this. Now we're going down the first row, so the next entry will be B times the 2 by 2 determinant, but it should be a negative on the coefficient of B. So this should be minus B times, now we're going down the first row here, the second entry in the first row, we need to strike out the row that B is in and the column that B is in. So what we'll end up having is the resulting determinant of whatever's left. In this case, it'll be minus B times the determinant of D, G, H, and K. All right, and then we're going to have one more determinant because we got to complete the row and the column. We got to complete the row, rather. So this was A, B, C, F, J, and since we're going down the first row, we got to do the C. Well, the coefficient, we need to take positive of the coefficient on C, so this will be plus C times, all right, now since we're dealing with C, we need to strike out the row and the column in which C occurs. It's going to be the resulting determinant of whatever's left, of D, F, H, and J. So what you end up getting in the end is the sum and difference of 3 2 by 2 determinants. So you would get positive A times the determinant of F, G, J, K minus B times the 2 by 2 determinant of what's left, and then plus C times the determinant of what's left. Okay? Now we can also go down a column, and you should get the same result. You may not see the exact same numbers here, the same letters here, but in the end you'll get the same result. It'll make more sense when we do actual examples. So I'm going to go down the first column this time. So I'm going to do the first number in the first column. That's still going to be positive of A times, okay, you still, if you go down the column, you strike out the row and the column in which it occurs. That would be plus A times the determinant of whatever's left, so that would reduce to a 2 by 2 determinant of F, G, J, and K. Now I've decided this time to go down the column, so we're going to take that approach. If I take the second entry in the first column, I'm going to pick D. And my coefficient on D should be negative. So that'll be minus D times a resulting 2 by 2 determinant when I strike out the row and the column in which D occurs. When I do that, I'll end up with a determinant B, C, J, and K. And then I'm going to do, I have to complete the column. So let's do that. So A, D, F, G, H. That means the last entry in the first column is H. And according to my coefficient determinant, that should be plus the coefficient on H times the resulting 2 by 2 determinant of what's left. So I strike out the column and the row in which H occurs. The resulting 2 by 2 determinant of what's left is going to be B, C, F, and G. So there's really several different ways you could do this. I could have gone down the second column, could have gone down the second row, could have gone down the third column, down the third row. But these are just two of the possibilities. I just wanted to show you it doesn't matter if you go down a column or a row. For a 3 by 3 determinant, you can even go down a diagonal, but once you get to 4 by 4 or greater, you can't go down the diagonal anymore. That's why I'm not teaching it to you that way, because I want to teach you to be able to do 3 by 3, 4 by 4, 5 by 5 by the same method. But in the end, it does not matter. You should get the same value for your determinant. That's all I'm really trying to illustrate here. So let's go ahead and do some actual 3 by 3 determinants. So I'm going to leave up my coefficient determinant. Let's see here. We have 2, -1, and 0. 4, 2, 1. 4, 2, 1. All right, so, and you're going to be happy with this trick because you are allowed, as I said, to find the determinant. You can pick any row or any column. Now let's look at something here. If we pick column 3, we go down the column, your first entry right away is a 0. And well, we know 0 times anything is 0, right? So here's what we can do. Let's say we're going to take the determinant of A. We're going to first convert all this into determinant form with that absolute value looking thingy there. So 2, 1, 0. 4, 2, 1, 4, 2, 1. All right, well, let's go down the first column. Not the first column, the third column. The first entry 0, and according to my coefficient matrix, that should be positive. But 0 times anything is 0, we don't have to screw with that. So we can go right to 1. According to my coefficient matrix, we need to negate the coefficient there, so that'll be -1 times the resulting determinant of whatever's left. Let's go ahead and strike out the row and the column in which that occurs. You'll end up with the resulting determinant of whatever's left. That'll end up being a 2 by 2 determinant. I probably didn't need to make it that big. Of 2, -1, 4, 2. And I'm going to have to rebuild this determinant here. The last thing we need to do is do that last one in the third column, which, since we agreed to do the third column, according to my coefficient matrix, I should put a positive on that coefficient of 1, so that would be +1 times the resulting 2 by 2 determinant of what's left when I strike out the row and the column. So that's going to end up then being the determinant of 2, -1, 4, 2. Now I only have to deal with 2 by 2 determinants as opposed to 3 of them had I gone down any other row or column. So let's go ahead and do this here. I'll have -1 times, what's a 2 by 2 determinant? So AD, so that would be 2 times 2. Let me use brackets here. So that would be -1 times the quantity of 2 times 2 minus that BC, so minus -1 times 4 plus another 2 by 2 determinant, plus 1 is just plus what's inside, so that would be 2 times 2 minus that -1 times 4 which would end up giving me the negative of what's inside of here. That'd end up being 4 plus 4 plus another 4 plus 4, which would end up being -8 plus 8, which would equal 0. So the determinant of A in this case is 0. Had I picked any other row or column, I would have got the exact same result. The only thing is, I would have been doing more work than I needed to. So you can look for rows and columns to make your life easier with the smallest coefficients or 0 entries. It's kind of one of those things of work smarter, not harder. You know what I mean? Work smarter, not harder. A use for determinants also is to determine if a matrix has an inverse, or invertible is another way to say it. If a matrix has a 0 determinant, that means it's not invertible. So there is no inverse for A because it's not invertible since the determinant is 0. So that can even save you some time from trying to find an inverse that simply doesn't exist. Let's do a couple more 3 by 3s, then we're going to do a 4 by 4 and even a 5 by 5. So let's pick another one here. We have -2 to 3, 1, -1, 0, 0, 1, 4. Alright, so we want to find the determinant of matrix A. So let's convert all of these entries into this absolute value notation looking thingy here. -2 to 3, 1, -1, 0, 0, 1, 4. Alright, so again, it doesn't matter what row or column you pick, but once you get started down that road, you need to stick to the same row or column. You have two good choices here. Both rows 2 and 3 have a 0, or you could argue both columns 1 and 3 have a 0. But if you take it by the row approach and call in row 2, the non-zero entries both have 1 coefficients, right? They have the coefficients of 1. Personally, my pick is going to be row 2. Let's deal with row 2. So if I start in row 2, you have a 1, but according to my coefficient determinant, I need to negate that 1. So that'll be -1 times the resulting determinant of what's left. So we strike out the row and the column in which that 1 occurs, you'll get the resulting determinant of a 2 by 2 of 2, 3, 1, and 4. And then with that, having said that, we only need to deal with one more 2 by 2 determinant because, let me rebuild this here. We decided we're going down row 2, and the third number is a 0, so we don't even got to bother with it because 0 times anything is 0. The next entry is going to be a -1. According to our coefficient determinant, we should take positive of -1, so that would be another -1 times the determinant of what's left. So strike out the row and the column in which that -1 occurs, you end up getting the resulting 2 by 2 determinant of -2, 3, 0, and 4. So now we can just solve these smaller 2 by 2 determinants. That'll be negative of 2 times 4 minus that 3 times 1. And then minus this determinant here, that would end up being -2 times 4 minus 3 times 0. So let's just do the multiplication. Let's do the order of operations. So negative of 2 times, let's see, 2 times 4 is 8. That'd be -3 minus, see, -2 times 4, that's -8 minus 0. So you'll end up with -5 minus -8. That's actually +8, which would give you a determinant of 3. So the determinant of matrix A is 3, which would mean, yes, it has an inverse. It is invertible. And had I done this with any other row or column, I would get the same answer of 3. I just might be doing more work than I need to do, or multiplying by larger numbers. Let's do one more 3 by 3, and then we'll go on to a 4 by 4, and even we'll do one 4 by 4, and we'll even do one 5 by 5. I normally don't like to do larger than 3 by 3, but I want to show you how higher order determinants work. So matrix A has entries -1, 2, -5, 0, 3, 4, 0, 0, and 3. Well, this is really sweet, because if we look at either column 1 or row 3, you could say both of those have 2 0 entries, right? So we're actually only going to be reduced to one 2 by 2 determinant. Now take your pick. You can have, for your 1 you're going to have to do, you can either, if you stick with column 1, you'll just have a coefficient of -1, or if you pick row 3, you'll have a coefficient of 3. It really doesn't matter. And you could pick any row or column, you just want to do the least amount of work. So let's find the determinant of A. My recommendation is, let's go for the smaller number. Let's go for column 1. So first, we're going to write this in determinant notation. -1, 2, -5, 0, 3, 4, 0, 0, 3. All right, now we're going down column 1. So according to my coefficient determinant, I need to do a positive of that -1. So that would just simply end up being -1 times the resulting determinant of whatever's left over when I strike out that column and the row in which it occurs, which would give me a 2 by 2 determinant of 3, 4, 0, and 3. And then notice if I'm sticking with column 1, the other two entries are 0, making any other determinants irrelevant. So we're just going to have to do 1 2 by 2 determinant. So this would be the negative of 3 times 3 minus that 4 times 0, which would equal the negative of 9 minus 0, or simply giving you a determinant of negative 9. So yes, this matrix would be invertible because it's not 0. You get a negative 9 determinant. And we only had to do 1 2 by 2 determinant in the end. And again, it doesn't matter what row or column you pick, you would get the exact same result. It's just with the least amount of work required. As I said, work smarter, not harder. All right, let's do a 4 by 4. I'm going to expand this to a 4 by 4 determinant. So as you see, for a 4 by 4, my coefficient determinant, I'm just going to simply, to the right of our 3 by 3, alternate the sign, a negative, a positive, and a negative. For higher order, just remember your signs alternate every other entry from positive to negative. That's really all you have to do. Let's pick a good 4 by 4 matrix here. And it's not going to be as bad as you think. Let's say I have a matrix 4 by 4 with entries 4, 0, 0, 0. Six, negative 5, 0, 0. 1, 3, 1, 0. 1, negative 2, 7, and 3. All right, so here's a 4 by 4 matrix that we would like to find the determinant of. Well, let's settle for the path of least resistance. Let's make our work easier for us. First, let's convert this into determinant form. We're going to take the determinant of A, which is going to be converting all this into this absolute value looking notation. All right, well, you notice if you either pick row 1 or column 4, both of those have 3 zeros and just one single non-zero entry. I'm going to pick row 1. We're going to make life a little bit easier. Because if we look at my coefficient determinant, that should be a positive on that 4, so it's going to end up being 4 times the result of when I take the column and the row in which that 4 occurs and strike it out. I'm going to get a 3 by 3 determinant as the result. That'll be 4 times the resulting determinant of what's left of negative 5 times 0, 0, 3, 1, 0, negative 2, 7, and 3. All right, there's my 3 by 3 determinant of what's left. Now, if I either pick row 1 or column 3, I have 2 zeros in each for the 3 by 3 determinant. So why don't we, once again, we'll pick row 1. So what's that going to turn into? This would end up being 4 times, let's do a big bracket here. I'm going to pick row 1. I'm going to use negative 5. according to my coefficient determinant, if I forget about everything here, I just look at the first, if I treat this as a 3 by 3, I should take a positive of that -5. So that would just be -5 times the resulting 2 by 2 determinant of what's left. So let's strike out the column in the row in which that -5 occurs. I'll end up with 1073. So this 4 by 4 determinant actually turned out not to be too bad. So let's go ahead now, let's work inside of our brackets. We'll have 4 times -5 times even smaller brackets here. A 2 by 2 determinant, you're going to have 1 times 3 minus 0 times 7. So this is going to turn into 4 times -5 times, let's see, 1 times 3 is simply 3 minus 0. So this would end up turning into 4 times -5 times 3, which would end up giving you 4 times -15, which would mean your determinant of A is going to be -60. So the determinant of matrix A in this case is -60. And we were able to do that with as little operations as possible. You could have picked any other row or column, you just would have been doing a heck of a lot more work than you actually needed to. But you should still arrive at -60 no matter which way you go for row or column. And we are going to do one 5 by 5. So if I do a 5 by 5, let's see, that's going to be I'm going to need to expand on a bit here. So there's my 5 by 5 coefficient determinant. So let's go ahead and set up this matrix here for the 5 by 5. So we have the matrix A has entries -2, 0, 0, 0, 0. -1, 4, 0, 0, 0. 3, 5, 1, 0, 0. And then we have 6, -11, 8, 10, 0. I should probably make space for one more. And then we have 0, 13, -9, 0, -3. So there's this hideous matrix A. It's a 5 by 5. Well, we want to find the determinant of A, right? So we're going to take all this, convert it into determinant notation. Yep, I know it's a lot of writing, but... Alright, let's really look at this here. We can go down rows 1 or column 5, and we have 4 zeros. Again, work smarter, not harder. I'm going to pick row 1. If I pick row 1, I'm going to have to deal with that -2 coefficient, and according to my coefficient determinant, I need to take positive of -2. So that'll be -2 of a resulting 4 by 4 determinant when I strike out the column and the row in which that occurs. The resulting 4 by 4 determinant is going to end up being 4, 0, 0, 0, 5, 1, 0, 0, -11, 8, 10, 0, 13, -9, 0, -3. I'm going to go ahead and shrink our coefficient determinant down to a 4 by 4 just to make life easy for us, because now we've been reduced to a 4 by 4. Alright, well, if we pick either row 1 or column 4 of the 4 by 4 determinant, you have multiple 0 entries. I'm going to settle for row 1. So we're going to take -2 times in brackets here. Let's pick row 1. We have the coefficient 4. According to my coefficient determinant, that should be positive of that 4. So we'll take 4 times the resulting 3 by 3 determinant of whatever's left when I strike out the column and row of what's left. So that'll be the determinant of 1, 0, 0, 8, 10, 0, -9, 0, -3. So we got this down a bit, but we still have a 3 by 3. So I'm going to go ahead and reduce my coefficient determinant one more time to a 3 by 3. Alright, so looking at this determinant here, I'm going to go with row 1 again. The non-zero entry is a coefficient of 1. The other two entries are 0. So this would equal -2 times the large brackets of 4 times some smaller brackets of 1 times the resulting 2 by 2 determinant of whatever's left, which would end up with a 2 by 2 determinant of, actually we probably don't even need those brackets, of, let's see, 10, 0, 0, -3. Alright, so now we've got this reduced down to a 2 by 2 determinant. So this is going to equal -2 times 4 times the determinant of what's inside. That'd be 10 times -3 minus 0 times 0. Alright, well 0 times 0 is 0. That's real easy. So this is going to be -2 times 4 times negative 30, well, inside the parentheses, 4 times negative 30, you'll end up having negative 2 times negative 120. Negative 2 times negative 120 gives you positive 240. So the determinant of matrix A ends up being positive 240. Had you picked any other row or column, you would get positive 240. It's just you're doing a lot more work than you need to. All right. I also would like to touch on some algebraic determinants. So you can also use determinants to solve for some algebra problems here. I'll demonstrate that. The goal is going to be to solve for x. Let's say you have a determinant x2, 1, and x, and that's equal to 8. Now actually, let's make that equal to 2. I was reading it wrong. Make that a little bit easier. So we have the determinant of x2, 1, and x equal to 2. Well, it's a 2 by 2 determinant that equals the value of 2. We're going to solve for x. We know the determinant of a 2 by 2 matrix is AD, so that would be x times x minus the b times c, so that would be minus 2 times 1. All that equals 2. So you would get x squared minus 2 equals 2. Well, you have a simple quadratic equation. That would be x squared equals 4, so x would equal plus and minus 2. Now, let's make sure both of these values check out since we're doing determinants. Well, if I set up the determinant, if I use positive 2, I'll have 2, 2, 1, and 2, which would end up giving me 2 times 2 minus 2 times 1, well, that's going to end up giving me 4 minus 2, which equals 2. So positive 2 checks out. What about negative 2? So put in negative 2 for x. So negative 2, 2, 1, and negative 2. What's that going to equal? That would be negative 2 times negative 2 minus 2 times 1. So that would end up being 4 minus 2, which equals 2, the original value. So yes, both solutions for x are going to be plus and minus 2. All right. Let's see here. We have x1, 2, x minus 2. The determinant of those equals negative 1. So let's go ahead and do our determinant. For a 2 by 2, we'll end up taking x times x minus 2 minus that 2 times 1, we'll have to set that equal to negative 1. So we'll end up with x squared minus 2x minus 2 equals negative 1, which should end up then giving us x squared minus 2x minus 1 equals 0. This is going to be a perfect square trinomial, which will factor into a binomial squared of x minus 1 squared equals 0. So x would equal 1. So we found the x value to end up being 1 in this case. And for good measure, let's do a 3x3 determinant with a variable. So let's see what we got here. You'll have 1, 2, and x. -1, 3, 2. 3, -2, and 1. All that is equal to 0. The bad news is we don't have any 0 entries in this determinant, so we're going to have to kind of stick this out and just go through the multiplication. If it helps you set up your coefficient determinant for a 3x3, that's going to be plus, minus, plus, minus, plus, minus, plus, minus, plus. The alternating positives and negatives. Any row or any column is as good as any, so why don't we go down the third column? So we're going to take, since we're going down the third column, we're going to take our first member of that, which would be x, and according to our coefficient determinant, it's going to be positive on that coefficient. So we'll have x times the resulting 2x2 determinant of what's left when we strike out the column and the row. So x times the determinant of -1, 3, 3, -2. Alright, so there's your first determinant. 1, 2x. Then we have 2 and 1. Just going to have to rebuild this a little bit. Okay, we're sticking with the third column, so now we need to deal with that 2 coefficient. According to my coefficient determinant, I need to negate that 2. So that'll be -2 times the determinant of whatever's left when I strike out the row and the column in which that 2 is. I'll have a resulting 2x2 determinant of 1, 2, 3, -2. And then I'll have one more determinant, x2, 1. Alright, so let's see. x2, 1. Then we have here -1 and 3. Now the last entry in the third column is a 1. According to my coefficient determinant, I need to keep positive of that 1. So that'll be plus the determinant of whatever's left when I strike out the row and column and where that 1 occurs. So I'll get a 2x2 determinant of 1, 2, -1, and 3. All that needs to be set equal to 0. So now let's just solve these 2x2 determinants. That'll be x times that -1 times that -2 minus that 3 times that 3. All that minus 2 times this determinant here of 1 times -2 minus that 2 times 3 plus this determinant of 1 times 3 minus that 2 times -1, all that equal to 0. So let's simplify all the brackets. You'll have x times 2 minus 9 minus 2 times -2 minus 6 plus 3 plus 2 all that equal to 0. Then you'll end up having, let's see, that would be x times -7 minus 2 times -8 plus 5 equals 0, which would simplify into -7x plus 16 plus 5 equals 0, which would be -7x equals -21, which would just give you that x equals 3. So we did all that work to get an x value of 3. But that's how the cookie crumbles. You'll get x equals 3. Alright, so I think that's it for this lesson. Next lesson's going to be Cramer's rule. We will talk about a method using determinants that we can use to solve systems of equations called Cramer's rule. So I hope everyone has a great day. Take care.